So I'm going to give the same pieces of advice I always give because it's still true. If you want to do well, make sure you do problems. And the more problems you do, the better you'll get. There's this review. We've also been doing reviews like this for the last couple of semesters, which means that you have a large amount of material to draw from. Now, keep in mind, if you go look at some of the older reviews, that they had different sets of topics for potential final exam problems. And not every final review problem really is appropriate, but a substantial number are, because there are really a strong collection of core ideas. And we want to make sure you know those. The more problems that you do, the better that you'll get. You'll start to develop a certain abilities to do problems, but also to sort of recognize. The hardest part about math is knowing what is the right thing to use in this situation. In some sense, you've gone to the point where, okay, I can do the computations, it's the setup. And to do the setup, I need to know what type of problem I'm doing. Well, that's where the doing the problems comes into play, because it really helps you start to recognize patterns. We'll try to highlight certain things as we go forward. The other thing, of course, is to take care of your health. We're coming up to final exam season. That's a very stressful time. Stressful mentally, stressful physically. Make sure you plan appropriately. Don't try to cram everything in the last 4 hours before the exam. The more you can spread the studying up over time, the better off you'll be. One of the reasons why we like to narrow down the topics is so that you can really have some idea of what to study, and it makes it slightly easier for you. Go out, take a walk. If you're outside, if you need to scream, there's lots of nice big open spaces on campus, and you can do that. So, with our advice out of the way, we begin. And let's start. So find the plane that contains the points 1, 0, 3, 0, 2, 1, and it never intersects with the line x equals 14t, y equals 27 minus 2t, and z equals 3t minus 137. So we're going back to the basics, because remember, this exam is comprehensive, start to finish. There will be topics from all 3 exams from this semester showing up. So, we're told to find the plane. So that's a key. We know we're looking for a plane. So, when we're looking for a plane, we know we need 2 pieces of information, and life is good. A point and a normal. And between these, the point is very straightforward. Almost always it's given. And when it's not, it's pretty easy to find. In this case, in fact, we have an abundance of points to pick from. Here we go, 103. Now you might say, how do I know it was a 103? What if I had chosen 021? Yeah, you'd still be good. All right, so we know 103. So that's not the hard part. The hard part is the normal. Now this is a vector, A, B, C. And that's going to be perpendicular to our plane. So what we've got to think about is, okay, how do we find this normal vector? And here's sort of the key idea. And this will get you through, I won't say every find a plane problem, but it gets you through a substantial number. And what you do is you say, let's find 2 vectors which are perpendicular to the normal. And the reason we do that is once we have 2 vectors that are perpendicular, then we can cross them together and we'll get our normal vector. Now, I really should say to get a normal, because there's more than one normal vector to a plane. There's many normal vectors, so we just need one of them. So we think of our geometry. So what we have is we have our plane that we're looking for. We have 2 points that are given to us. And then we have a line. And we're told that our line never intersects the plane, so that never crosses. And what we want to do is extract enough information to figure out, all right, what are some vectors? So what we look for is we look for vectors. Now, line, you can get a vector for a line fairly easily, which is the direction of the line. Now, the direction of the line, the question is it perpendicular? And the answer is yes. If a line and a plane don't intersect, that says that the line has to be parallel to the plane. So this direction has to be the same. You can almost think of it as if you could cast a shadow down into the plane. It has to be a direction in the plane. So one of our vectors is the direction vector of the line. Now, how do we get the direction vector of the line? Well, if we write our line like negative t plus 14, y equals negative 2t plus 27, and z equals 3t minus 137, it's the pieces in front of the t. So the direction vector of our line is minus 1, minus 2, 3. Now, a second direction, we can recover that by saying, well, we got 2 points, and just make a vector. Because the points are not vectors. So don't say, oh, I'll just cross 1, 0, 3 and 0, 2, 1. Those are not points. Sorry, those are not vectors, they're points. You can't just cross them. But if you go from 1, 0, 3 out to 0, 2, 1, so there's, let's say that's 1, 0, 3. Let's say that's 0, 2, 1. Then I can take the vector that goes between them, and that vector, well, I go down by 1, so negative 1. I go up by 2, and then I go down by 2. So there's our another vector. Any vector that's in the plane has to be perpendicular to the normal. So now we have our 2 vectors. They're not the same. That's good, because if they were the same vector, we'd be in trouble. And now, to finish this, we need to cross I, j, k, minus 1, minus 2, 3, minus 1, 2, minus 2. So we should be comfortable taking our cross products by now. 4i minus 3j minus 2k minus another 2k minus 6i and minus 2j. So it looks like negative 2, negative 5, negative 4. Now, I say it looks like I did that kind of quickly, and I'm always paranoid that I got the right answer. You should be. I mean, this is the final, your last chance. You want to make sure you get as many points as you can. So we check the dot products, right? So let's say with the dot products here, we get 2 plus 10 minus 12. 0. Good. 2 minus 10 plus 8. 0. Good. So that is perpendicular to both. So that means we probably did it right. So this is our normal. This is n. So once you have your normal vector, which, by the way, we can scale it, so I can get rid of the negatives. So I can pick 2, 5, 4. Because I really just need it up to some factor. So that says that these 2, 5, 4, these are like the coefficients for our plane. 2x plus 5y plus 4z equals something. So we're really close. We just have to finish with the equals something. And that comes from the point. So we have 2 times 1 plus 5 times 0 plus 4 times 3. Well, that's 2 plus 0 plus 12. So it better equal 14. And that's the answer. We're done. All right. Well, that's a nice warm-up. Are they all going to be this good? You're probably thinking, that seems a little bit easy. Well, the problems on the final are not meant to be hard. I think what makes the problems on the final seem hard is just there's so many topics. And if you practice, life is good. And we'll make good progress. Okay. So, next one. Find the integral from 0 to 1, integral x to root x, of 30x cosine of 5y cubed minus 3y to the 5th dy dx. Now, we look at this and we say, oh, okay, it's just integration. Integrate one layer at a time. Life is fine. But then we say, I don't think I'd actually want to integrate this with respect to y, because it looks like cosine 5y cubed minus 3y to the 5th. I'd have a really tough time of doing that. So I'm not going to do that. All right, so what can we do instead? Well, what we can do instead is the following. We can say, all right, so let's integrate not with respect to y first, but with respect to x first. And in order to do that, we need to sketch our region. So we think of our bounds. Our bounds say that currently we go from x to 0 to 1. And for y, we go from x is the bottom up to square root of x is the top. So we sketch that. Y equals x. And then we get y equals square root of x. And it's actually pretty easy to see that if you plug in 1 into either x or square root of x, you'll get the same value out. You get 1 out. So our region is this sort of little bit of a sliver here. That's our region. Okay, so that's what we want to change. And we want to change our order of integration. So we say, all right, we need to switch it. Well, we look for where does y go from. I go from the lowest value of y is 0 to the highest value of y, which is 1. So 0 less than or equal to y less than or equal to 1. And originally, when I was doing with respect to x, I was doing it up and down. Now, I'm going to be doing left, right. So I want to say, okay, I'm going from the low value to the high value. In particular, I need to solve for x. Well, that's not so bad. Y equals x becomes x equals y. Y equals square root of x becomes x equals y squared. So I'm going to go from the left side, which is y squared, to the right side, which is y. So my integral becomes integral 0 to 1, integral y squared to y of 30x cosine 5y cubed minus 3y to the fifth dx dy. Now we integrate. And here, when we integrate with respect to x, life is a lot better. Because what's our function? The cosine 5y cubed minus 3y to the fifth, that's a constant. That's easy. So the only place x shows up is here. Integrate with respect to x, and you're going to get 15 times x squared. So 15x squared cosine 5y cubed minus 3y to the fifth. Evaluate that from x equals y squared up to x equals y. And if we do that evaluation, that becomes the integral of 0 to 1 of 15 times y minus y to the fourth. And then we have a cosine of 5y cubed minus 3y to the fifth. Oops, sorry, I forgot the square. Y squared, yep, dy. Now from here, you might see, well, it still looks terrible, but maybe this is helpful. If you set the inside part to u, you'll see that du is 15y cubed, y squared. I can't read my handwriting there, that's a cubed. So 15y squared minus 15y to the fourth dy, which is exactly what I have. So this becomes the integral of cosine of u du. Well, where does u go from? Well, when I plug in 0, I get 0. If I plug in 1, I get 5 minus 3, which is 2. So this is sine of u from 0 up to 2, which becomes sine of 2. So this is a problem where it's really testing you on changing the order of integration. And how do you recognize it? Well, basically, if you have an integral that you have to do, and you're like, I can't do the integral in the order it's actually been given to me, but if I change the order, life is good. So be open to having to change the order. All right. So, number 3. Let S be the solid box where we have 0 less than or equal to x less than or equal to 1, 0 less than or equal to y less than or equal to 2, and 0 less than or equal to z less than or equal to 3. So I have this big box here. And here we go. Here's our solid box, S. We probably don't need to draw. I think we all know what a box looks like. Now let this symbol, whenever you see this symbol, the first part of the course, or earlier in the course, we thought of this as the partial symbol, but in the latter part of the course, it became another use. It became the boundary. So when you see this, we think of this as the boundary of S. So this is the bounding surface of S. And moreover, when we talk about surfaces, we like to orient them. And so when we have a surface of a solid, we have what we call the outward pointing normals. So that means that we will point straight out from the sides of the box. So these are our normals. It just depends on which face we're on as to which way we point. Okay, so we have an oriented surface. And here's the question. Find the flux through the boundary of the surface for the vector field F, which is this crazy looking function. Now, at this point, you're probably like, I don't know if I've seen this before. And the answer is, you haven't seen this before, because we haven't covered it yet. Because remember, we still have like a few more lectures. But I'm going to tell you right now how it works. And then we're going to say, like, why did you wait to the last lecture? You should have started with this on day 1. This is so much cooler than like all the stuff we've done in the last 15 weeks. I know. I get where you're coming from. So let's talk about what's happening here. So this is what's called the divergence theorem. And what does the divergence theorem have to deal with? Essentially, the divergence theorem is flux through a surface of a solid. Now, how do you know if you're in a problem that involves a divergence theorem type question? There's a couple things you look for. You look for a flux, and you look for a solid. Okay, once you have that, you're good to go. Now, sometimes it doesn't actually use the word flux. The way that it might show up as flux is it says it's the integral on the boundary of f dot n. This is what the flux is. So it might use the word flux, or it might say, here's this integral. Certainly, there will be a solid involved. So once you have that, the divergence theorem says, oh, the flow is equal to the integral over the whole solid of the divergence of f dv. That's the divergence theorem. We actually saw a special case of this. If you took Green's theorem and you did the analogous thing in 2 dimensions, you can say that the flow through a 2-dimensional region, if you take the flow at the boundary, that's equal to the integral over the interior of the divergence. That's something we showed. So this is the divergence theorem. So what does it say? Well, it's saying that what we want to do is we apply divergence theorem, and what we want to find is the integral over our whole solid of the divergence of f. So that's what this problem has become. And one of the clues that should give you an idea that you don't want to do the problem as it's stated is we're trying to make things look uncomfortable. And this part right here, that log expression, that looks terrible. And usually if you see something terrible, that's a symbol that you shouldn't do it, that there's a better way. So in our case, we say, all right, let's apply this result. So this will be the integral over our solid. Now remember the way that divergence works. It says you're going to come up with a function. The function is the output. In the first entry, you come to and say, take the derivative with respect to x. So my question to you, what's the derivative with respect to x? 0. The bad stuff goes away. Second entry, derivative with respect to y? 5. Last entry, derivative with respect to z? Y e to the xy. All right. Well, that's not completely gone, but in relation to what we've had to do before, not so bad. Okay, and that's dv. Now, the original sounds terrible. This one seems like, yeah, it doesn't seem so bad. So for instance, there's really 2 pieces. There's 5, the integration over our solid dv. We'll talk about that. And then there's plus the integration over our solid of y e to the xy dv. Well, let's do the first piece. How do we find this? Well, if you just integrate 1 dv, what are you finding? Volume. So we come to our box. Well, it's a 1 in the x direction, by 2 in the y direction, by 3 in the z direction. So the volume is 1 times 2 times 3. So this will end up being 5 times 6, or 30. Now for the last one, well, That one we actually have to integrate. Now, so we'll integrate this in layers. So we come and ask ourselves a question, well, what's the right order of integration? So y e to the xy. Well, first off, the dz doesn't really matter. We might as well just do that early on, get that out of the way, since there's no z in there. Is it better to integrate first with respect to x or with respect to y? Yeah, because if you go with respect to y, run into troubles. Integration by parts, crazy fractions, and life gets messy. 0, 1, 0, 2. And so we start working our way through here. So what do we get? Well, when you integrate with respect to z, you'll get, well, you'll just add a factor of 3. There's nothing really happening here. It's just a constant. So we'll end up with 3, integral 0 to 2, 0 to 1, of y e to the xy dx dy. When we integrate the inside with respect to x, what do we get? Well, e to the xy. And evaluate from x equals 0, x equals 1. So that's 3 integral 0 to 2 of e to the y minus e to the 0. Okay, so that's 3. Integral of e to the y is e to the y, and minus y. Evaluate that from 0 to 2, and we're almost out of space, but that's okay, we're almost done. So that's going to be 3 e squared minus 2. Then I'm going to subtract. E to the 0 is 1 minus 0. So I have 3 times e squared minus, all right, it's 3e squared and minus 9. So if we combine that with the 30, we get that our total answer is 3e squared plus 21. Okay, now these problems are actually pretty straightforward once you know the right tool, and the tool is divergence theorem. So we're going to get a lot of practice this week. We're going to have a whole day for divergence theorem, and then another day where we just do practice with divergence theorem, and another topic, Stokes theorem, which we'll get to probably pretty soon. And so there's, once you know to apply it, there's really no big surprises. Now I'm going to ask a question. What this is measuring is flow. Does the output need to be positive? No. It's perfectly okay to have negative output. So don't get nervous if at the end of it you're like, oh my gosh, I got a negative number. No, you'd be like, yeah, negative, whatever. I can deal with it. Okay, number 4. Show that the following vector field is conservative. Okay, well that's one way to do it. All right, so I have a vector field and I want to show it's conservative. And I say, no problem. I just have to find the antiderivatives, and then I'm good to go. Antiderivative of 1 over x squared plus 1? Yeah, arctangent. Yeah, that's easy. And antiderivative, and of course we're talking about antiderivative with respect to x. Antiderivative with respect to x of 2xy e to the x fourth y squared is, of course, not something we want to do. In fact, you probably have a really hard time doing it because you can't do it. All right, well that puts a damper on things. All right, so what does that mean? Is it not conservative? Well, remember, finding a potential function is not what you need to show that something is conservative. To show something is conservative, yes, definitely. If you can find a potential function, do it. But just because you can find a potential function doesn't mean it's over. What can you do? Well, if you have an m and an n, you are conservative if and only if you come to m sub y and you compare it to n sub x. If they match, you have to be conservative. So let's actually do this computation. So what is m sub y? Well, so we're not going to do this anymore. Take the derivative of 1 over x squared plus 1 with respect to y, you get nothing. Go to the second term, take the derivative of that with respect to y. You have to do a product rule. So you get 2x plus, because the derivative of the first would be 2x, 2x, not plus, 2x, and then e to the x to the fourth y squared, sorry about that, plus 2xy times the derivative of e to the x to the fourth y squared, which is e x to the fourth y squared, times by x to the fourth times 2y. Okay, that's the derivative of the second term. On the other hand, you get n sub x. What is that? Well, that second piece goes away. Well, the first piece, well, you take the derivative of the first, which would be 2x, e x to the fourth y squared, plus the first times the derivative of the second, which is e x to the fourth y squared, times, here, it'll be 4x cubed y squared. Now what we do is we just do a comparison. We say, okay, well, the first pieces obviously match, and the second pieces, well, we get 2 times 2, that's 4, that's good. Here I have x to the fourth, that's x to the fifth. Y and y is y squared, and those parts match, so these are equal. Which means f is conservative. All right, so we now know that the function is conservative. Now we hit part B. Well, suppose you have this crazy curve. And here we're going to use the same function as from part A. And what we want to do is we want to say, what is the integral along the curve of f dot dr? Well, remember, one way to find this integral is to find the potential. That's not going to happen. We got stumped. Maybe we didn't try hard enough. No, we got stumped. All right. So, is there anything left for us to do? Well, let's think about this curve. Where do we start? At time 0. Well, we plug in 0. Sine of 0. And then we're going to get 0, 0, 0, cosine of 0, which is 1, minus 1, which means that we're starting at 0, 0. Where do we end? Plug in 1. We get sine of 7 pi, which is 0, 1, minus 1, plus 1, plus cosine of 8 pi is 1, minus 1, which means that we're going to end at 0, comma 1. So our curve currently goes between those two places. Now, it kind of does some sort of going back and forth, something like that. I don't know exactly, but it definitely doesn't go there in a nice straight way. Because it's conservative, what are we allowed to do? Yeah, we can create our own line. We can choose a better curve. What's a better curve that goes from 0, 0 to 0, 1?
0,
Yeah, 0, comma t. I should have said there's an arrow here. So we have a chance to do a parameterization, 0, comma t. So what do we get? Well, this is going to be, again, I'll write out what this becomes. Integral along the curve of our 1 over x squared plus 1 plus 2xy e to the x to the fourth y squared dx plus x squared e to the x to the fourth y squared, sorry about that, plus 2y over y squared plus 1 dy. That's just what FDR means. Now, notice on our curve, x is always 0, so anything with an x attached to it goes away on our new curve. And so what we end up with is this becomes the integral from 0 to 1, because that's our parameterization. We should have written down that 0 less than or equal to t less than or equal to 1. 0 to 1 of, and now everywhere we see a y, that becomes t. So it's 2t over t squared plus 1. dy is 1, because y prime is 1, and then we put a dt on the end. So that's a really easy integral. So by choosing a nice curve, now we have an easy integral. The integral of 2t over t squared plus 1? ln of, t squared plus 1. And evaluate from 0 to 1. And if you plug that in, you get log of 2 minus log of 1, but log of 1 is 0. So our answer is log of 2. Just like we would have thought when we started. No. We probably thought we can drop 1. No, we would never think that. We're going to go all the way. All the way. Number 5. A plane is tangent to the surface z equals 1/3 x cubed plus 1/2 y squared and perpendicularly intersects with the line 4 plus 2t, 3 minus 2t, minus 1 minus t. Determine where the line and plane intersect. So I have this surface, and if you look at it, it looks a lot like a bowl, but it's not a perfectly round bowl. It seems to be it's stretched a little bit more in a particular direction. So it's a little bit more of a sort of elliptical bowl. Okay, but I have this bowl shape. And I have that there is a plane which is tangent to this surface. And I'm told that it perpendicularly intersects with this line. So I want to figure out where do the line and plane intersect. So I sort of have to unravel this and think about what are my pieces. I know I have a plane, but it's not just any plane, it's a tangent plane. And I'm after a tangent plane which has a very particular property. So there's lots of tangent planes. I want the one which is perpendicular to this line. Well, again, I look at the line and say, let me look at the direction of the line. The direction of the line would be the vector that corresponds to the parts with the t. So that would be 2 minus 2 minus 1. That's the direction of the line. So I'm looking for a tangent plane to this surface where this would be a normal vector. So when I'm after a tangent plane with a certain property, here's my basic idea. Let's find all the tangent planes. Because if I can find all the tangent planes, certainly the one that I need will be among that list. I'll probably want to focus my attention down and narrow it down a little bit, but certainly the one I need is on my list. So what's the tangent plane formula? So it's z is equal to FAB plus f sub x at AB times x minus a plus f sub y at AB times y minus b. And we will very likely write this formula down multiple times today because the tangent plane is a very important idea when we talk about Calculus 3. It really helps sort of drive what's going on. So let's see what we have. So looking at this, our function right now, our function f of xy is 1/3 x squared plus 1/2 y squared. So if we take f sub x, that would be 2/3 x. And if we look at f sub y, that would become y. So we get that z is equal to, I plug in ab, so that's 1/3 a squared plus 1/2 b squared. That's the f of ab. Plus f sub x at ab. So if I plug that in, I'll get 2/3 times a. And multiply that by x minus a. And f sub y at ab, well, plug that in, I'll just get the y, which is b, times y minus b. Now, at this point, we can rearrange. In fact, we're going to rearrange. And let's move stuff around. So, we'll get z equals, I'll have 2/3 ax, and I'm going to have plus b times y. Now, the rest of it. Well, I have minus 2/3 a squared plus 1/3 a squared, so that's minus 1/3 a squared. Here I have a half b squared minus b squared, so that's minus a half b squared. All right. Well, let's move the z over here, and let's move the constants over to the other side. So that if we do that, we get that our tangent plane has the following form. It looks like 2/3 1/3 a squared plus 1/2 b squared is equal to 2/3 ax plus by minus z. So in particular, this is the tangent plane at a point a comma b. I don't know what a and b are. I just say if I have the tangent plane at AB, this is the actual tangent plane written in a nice plain format. Well, now we say, hey, wait a second, let's read off our normal vector. Now that we've written it like we would write a plane, the normal vector, that's our coefficients. So the normal vector, that's going to be 2/3 times a, b, and -1. Now we start trying to piece together the information. The line has to perpendicularly intersect the plane. That means that the direction of the line is perpendicular to the plane. So this is also a normal to the plane. In other words, the direction of the line is a normal to the plane. So now, what does that tell me? Well, it tells me that these two vectors have to, up to a constant, be the same. Now, very lucky for us, our constant is just 1 because already the z components have to match. So since the z components have to match, that means the x and the y components have to match. So we can conclude that 2/3 times a has to equal 2, and that b has to equal -2. Well, from here, it's not too hard to solve for a and b. For instance, a equals 3, and b, well, we already know what b is. It's -2. So that tells us where the point of tangency happens. Now, at this point, you're like, are we done? And the answer is no. Because what are we looking for? We weren't looking for the tangent plane. We need that information. We were looking for a very particular thing. It says, determine where the line and plane intersect. So if I'm looking for where the line and plane intersect, what does my answer have to look like? It has to be a point. My final answer when I finish this problem and I circle something at the end, it's going to be a point. So I'm looking for a point. But now that we know the point of tangency, since we know a and b, let's update our plane. So we're going to take 1/3 times a squared. So that's 1/3 times 9, which is 3. And 1/2 times b squared. So that's b squared would be 4. And take out that is 2. So we're going to get 3 plus 2. So we get that 5 is equal to, and now what's our normal? Well, we actually know that we can use the same normal because we already know that 2/3 times a is 2. So that's 2x, and then minus 2y, and minus z. So this is our plane, which perpendicularly intersects the line and is tangent to our surface. Now we just find where the plane and the line intersect. So to do that, we say, hey, up here, x is 4 plus 2t, y is 3 minus 2t, and z is minus 1 minus t. Those are our x, y, z for our line. We want to find the point on the line which is in the plane. So I can replace x by 4 plus 2t. I can replace y by 3 minus 2t. And I can replace z by minus 1 minus t. So if we do this, and we're careful with our math here, let's say we're going to get 8 plus 4t minus 6 plus 4t plus 1 and plus t. So let's see, we get 4 plus 4 plus 1 makes 9t. Then we have 8 minus 6 plus 1. So that would be 3. So 5 equals 9t plus 3. All right, so that tells us that 9t had better equal 2, or that t had better equal 2 ninths. Well, how do I use that? Well, that tells me that's the time when my line is going to hit the plane. So the last thing I need to do to get my final answer is to do what? plug 2/9 back into t. So we'll get 4 plus 2 times 2/9. I'll just write this as 4 plus 4/9, which is 40/9, but you don't have to simplify. Then 3 minus 4/9. And again, you could simplify and say I think it's 23/9, but you don't have to. And minus 1 minus 2/9. And whoops, that's not a vector, that's a point. So that is the point where we intersect the plane. Plug into the line. There we go. So that's our final answer. 4 plus 4/9, 3 minus 4/9, and negative 1 minus 2/9. These problems are fun. Is it all coming back now? She's like, good stuff, good stuff. Cool. Well, don't worry. We have plenty of problems left, and hopefully enough time. Let S be the oriented surface, x squared plus y squared plus z minus 3 squared equals 9, with y less than or equal to 0, with normals pointing in the positive y direction. Let partial S, or boundary S, I'm always tempted to say partial, but okay, boundary S is the bounding circle of S. Find the integral on the boundary of S of negative 6z, comma x cosine y squared, comma 5x dot t ds. Okay, so what's happening here? Well, if we think about our shape, what do we have? X squared plus y squared plus z minus 3 squared equals 9. Well, that's what?
A sphere with radius of 3 shifted up.
Right. So we have a sphere with radius of 3 shifted up by 3. And it's the shell. It's not a solid sphere, it's a shell. Because it's an equality. If we had a less than or equal to, it'd be the whole thing. But then we're told something else. We're told that y is less than or equal to 0. Which means that we're going to take our sphere and we're going to cut it in half. And in particular, we're only keeping the half where we are less than or equal to 0. So it's this back half here. So I want to color in a slightly different hue one part of this. So there's this piece here. This piece here, that's in the xz plane. That part is the boundary, because that is a circle where I have y equals 0 in this shape. All right, so now what are we trying to do? Well, we're trying to do the integral on the boundary. Now, if you look at this problem and you were to channel your third exam knowledge and you saw this, what would you think? Closed curve, you're integrating on it. What do we do? Green's theorem. Well, that was a nice two-dimensional thing. So the question is there a three-dimensional thing? And the answer is yes. It's called Stokes Theorem. So Stokes Theorem, this is equal to the 3D version of Green's. Now, how does Stokes Theorem work? Well, Stokes Theorem, and again, this is something we're going to talk about next week, and I apologize, this is going to turn into a mini 5-minute lecture. Go ahead and don't fret too much if you don't catch it right now, because you're going to get a chance to catch it later. So what Stokes Theorem says is, suppose you have a boundary. Has an edge. Sorry, you have not a boundary. You have a surface with a boundary. So in other words, there's an edge on your surface. And there's an orientation. Now, what happens when we talk about orientation, there's really two aspects of orientation. Because when I talk about a curve, that can be oriented. When I talk about a surface, and the way we orient on a curve is how do we travel on the curve. Because you can imagine traveling in two different directions, depending upon which way you want to go. When you talk about a surface, you're saying, which ways do your normals point? Well, notice it tells us that our normals, so if I take a point here, I could be pointing in two different directions perpendicular to the surface. I want the one which has positive y direction. So my normals tend to point in the positive y way. So I just want to have an orientation. So if I have all of this, then what I can conclude is that the integral on the boundary of my surface of f dot t ds is equal to the integral on my whole surface of the curl of f dot n dsa. In particular, it's a flow type problem. Now, the thing that makes Stokes theorem intimidating is, like, in some sense, neither one seems like a great option. You got to do a line integral, or you have to work with some unpleasant surface. And surface integrals are not always fun. But there's this really cool aspect. And so there's three options as to how to do a problem that involves Stokes theorem. Option number one is do the actual line integral. Option number two is to do the actual surface integral. And option number three, and I'll write it down first, is to do the following. And I probably shouldn't use T. Let's use, I'll use capital F. There we go. Is to do that surface integral. Now, I have to specify where F and S have the same boundary. Okay? So what that means is change your surface. If you don't like the surface that the problem gives you, don't use it. Use a better surface. Now go back to a problem we did just a few minutes ago in your head. Remember we talked about you have a conservative line integral. You said, well, look, maybe the curve is bad. Well, don't use that curve. Choose a better curve. So in our case, maybe our surface is bad. Let's choose a better surface. The only thing that has to be true is I have to find some surface with the same boundary. So let's think about our current boundary. If we look at our boundary, what does our boundary look like? Can you see it? Our current boundary is that circle. All right. Can we think of a surface whose boundary is that circle, which is much easier to work with? You see one? Just, yeah, fill in the circle. Make it flat. And this is sort of like you're popping the bubble, right? And it collapses down. That's what we're doing. We just want to make it, and we say, hey, here's a better surface. So if this was our original surface, S, here's our new surface, F. Now, what makes this new surface highly attractive? Well, look at our new surface that you have here. This surface is entirely inside of the xz plane. So, what happens to your normal vectors? Well, the normal vector in your original surface was all over the place. It points in all sorts of different directions. And here, where's your normal vector? It's always going to point in the same way. So the normal vector is 0, 1, 0. So this is a constant normal vector. So by simplifying your surface, your problem becomes substantially easier. It's a little bit of a smaller challenge. Okay, so we will now proceed as though we've had all this background material, and we're going to say, all right, cool. So here's my preferred way to do it. If I see a surface, I say, look, can I flatten my surface? A flat surface is a happy surface. We like flat things. So I flatten it, and this one I can. And when I see it, I say, oh, I'm going to use this new surface. So according to this, I'm going to take the integral on the surface, the curl dot n. So I need to compute the curl. So I'm going to take del cross minus 6z x cosine y squared and 5x. By the way, this symbol is called del. Sometimes it's called nabla. So when we do this, we're going to get something. Now, out of curiosity, can you see, this is going to sound strange. Do we need to compute all of this? So, I claim that with our original surface, we need to compute all of it, because our normals will, again, point in all sorts of different directions. But look at our new surface. We're going to end up taking it dot 0, 1, 0. If I take it dot 0, 1, 0, well, 0 is really hard to recover from. So do I care about the first and the third entries? At the end, they're going to be zeros. So what I'll do is I'll say, look, I don't know what the first entry is. I'll put a star. I don't care. Let me go to the second entry. So that would be j, partial z, negative 6z. So that way would be negative 6. And here I'd have partial x of 5x, but notice I'm going in that wrong direction. So I should subtract that. So derivative with respect to 5x, derivative of 5x with respect to x, excuse me, I'm sorry. Okay, so that's what we get in the second entry. The last entry is something we don't need to worry about it. Because what's going to happen? So we get that this is going to be equal to the integral along our boundary of S of minus 6z x cosine of y squared 5x dot TdS is equal to the integral on our surface of something, negative 11 something, dot 0, 1, 0, dSA. When I take this dot product, what comes out? Negative 11, which is a constant, which means we can pull it outside of the integral, and we get the integral of our surface dSA. If I integrate on my surface dSA, what have I found? I found the area. And I realize now I have a small typo. This should have been F, because we've switched to our new surface. So I just need to figure out what's the area of this surface. Well, let's figure out, we said it was a circle. How big is this circle? Pi r squared. What's r? 3. So we get negative 11 times 9 pi, which means that our answer is negative 99 pi. And that's the answer. So you'll notice that essentially most of the work was really down here. This is just sort of the background. And the other part of the work was to say, simplify what you're working with. A simpler surface makes life better. And try to make things flat. If you leave calculus, and hopefully this is like your calculus graduation ceremony, this final exam. If you leave calculus, I hope you leave with the understanding that flat things are nice, and you should always prefer to work with a flat thing when possible. Use the linearization of f of xy equals xy e to the x minus 2 plus 4 sine of y plus 1 minus 3y log of x squared minus 3 at the point 2 comma negative 1 to estimate f of 2.1 comma negative 1.1. Now, there's a couple of key words here. First off is the word linearization. That's just a fancy way of saying tangent plane. So when you see linearization, think tangent plane. It's the part, or rather, I should say, it's the flat thing which best approximates the function nearby. When you see the word estimate or approximate, you think plug something into the tangent plane. So what this question is asking us to do is it says, let's find the tangent plane at 2, negative 1. And then, once you have that tangent plane at 2, negative 1, plug in the point 2.1, negative 1.1 into that plane. And whatever comes out, that's what you want. So this is what the problem is telling us to do. So when you understand how the problem asks us to do things, then we say, okay, now we'll just do them. So let's do that. So we take our generic formula, which, by the way, let's write it down. It's f of ab plus f sub x at ab times x minus a plus f sub y at ab times y minus b. So remember, that's our generic formula for a tangent plane. So we're going to need our partial derivatives. So let's look at f sub x. So that's going to be product rule in the first term. So it'll be the derivative of the first, which is y, e to the x minus 2, plus xy times the derivative of e to the x minus 2, which is e to the x minus 2. The second term, there's no x, so that goes away. The last term, the 3y is a constant. When we take the derivative here, we're going to end up with a minus 6xy over x squared minus 3. The additional factor of 2x coming from the chain rule. When we take f sub y, from the first term there's only one y, so we end up getting e to the x minus 2. The second term, well, that would be 4 cosine of y plus 1. And the last term, there's again just a single y, minus 3 log x squared minus 3. So there's our f sub x and our f sub y. Now we've got to plug everything in. So we plug in f2 negative 1. So we'll plug it in along here. So here I have e to the 0 times 2 times negative 1. So the first term will be negative 2. Next I'm going to have 4 times sine of 0. So that's going to be 0. Then I'm going to have a plus 3 log of 1. The log of 1 is 0. So our function is negative 2. So that's at 2 negative 1. Now plug that into our partial derivatives, f sub x at 2 negative 1. So we're going to have negative 1 times e to the 0, so that's minus 1. And then here we're going to get negative 2 e to the 0, so minus 2. And then over here, the denominator will become positive 1. And then here we're going to have minus 6 times minus 1 times 2, which would make that plus 12. All right, so that would make the grand total there 9. F sub y at 2 negative 1 would be, okay, plug this in. We get 2 e to the 0, so that's a positive 2. Then we get 4 cosine 0, well, that's positive 4. And minus 3 log of 1, that's 0, so that goes away, so we get 6. So that tells us that our linear approximation, which I can write that as L of x as our linear approximation, which is our tangent plane, it's the function, which is negative 2, plus the derivative with respect to x, which is 9 times x minus a, plus the derivative with respect to y, which is 6 times y minus b. So that's the linearization. And oops, I said x. I'm sorry. I should have said L of x comma y, because it's multivariable here. So now, what's the point? Well, the point is that the function is approximately the linearization. And so the function at 2.1 comma negative 1.1 is approximately what happens when you plug 2.1 negative 1.1 into the linearization. So that is negative 2. Why did I put a and b here? I am so sorry. It's been a long day. That should be x minus 2 and y minus 1, so y plus 1. There we go. I do apologize. Negative 2 plus 9 times 2.1 minus 2 plus 6 times negative 1.1 plus 1. And that's one of the reasons, by the way, you don't want to expand the linearization out, because if you're planning to plug things in to do an approximation, it's better not to expand, because now you'll see that, hey, these pieces are much easier to work with. 2.1 minus 2 is 0.1. Negative 1.1 plus 1 is negative 0.1. So we're going to end up with negative 2 plus 0.9, and then we're going to get here minus 0.6. So our net contribution is negative, or sorry, 0.3 positive, and then we have a negative 2, so negative 1.7. And that's our estimation. All right. Now, of course, you can always do better, but that would require us to do Taylor polynomials, and that's not on the test. So, woohoo! So we can stop there. All right. Good. Now on to another fun topic. So we have the position of a particle. It's given by r of t, which is this expression here. And we want to find a sub t and a sub n, the tangential and normal components of acceleration. So how do we do it? Well, the way to do it is, well, there's two ways. So here's sort of an overview. There's the geometric way. So the geometric way says the following. If I want to find a sub t, what I'm really after is I'm looking for a projection of a sub t of acceleration onto motion. So you would take r double prime dot r prime, and you divide it by the magnitude of r prime, and that would be your a sub t. To find the normal, you want to find something which is perpendicular. So how much of acceleration is perpendicular to motion? And that comes from the cross product, r double prime cross r prime over magnitude of r prime. That's a sub n. So that's if you do it geometric. Now, I prefer algebraic if things are easy. And almost always algebraic is the better way to go. There are some cases where geometric is more useful, in particular if you're looking at a particular expressed point, then the algebraic can be much worse. So how does algebraic work? So if I want a sub t, what we do is we take the derivative of the magnitude of r prime. So you find the magnitude of r prime, you take that derivative, there's your answer. Well, how do you get a sub n? Well, to get that, you make the following note. A sub n squared plus a sub t squared is equal to the magnitude of r double prime squared, which is really acceleration. So this is Pythagorean theorem. It says that if I want to know what's happening with acceleration, I just break it into two parts. And therefore, if you rearrange, you get a sub n is the square root of the magnitude of r double prime squared minus a sub t squared. Okay, so that's the algebraic. And again, I prefer algebraic whenever possible. So let's find out if something happens that's nice. So we start with our r, and the first thing is you've got to compute r prime. And it's always the first thing, regardless of which choice you go. So we compute r prime. What do we get? Well, take the derivative here. We'll get t to the fifth, comma, 2t to the fourth, comma, 2t cubed. So there's our r prime. Now we take the magnitude of r prime, which is going to be the square root of t to the fifth squared plus 2t to the fourth squared plus 2t to the third squared. So to find the magnitude of r prime, you take each entry squared, add them up. So at this point, it's not so clear if we're going to succeed here. So this is what? T to the 10th plus 4t to the 8th plus 4t to the 6th. But what can you do? Well, notice everything has powers of t. Let's pull up the highest power we can. That's t to the 6th, and then you get t to the 4th plus 4t squared plus 4. Well, the square root of t to the 6th, that's t cubed. But what about t to the 4th plus 4t squared plus 4? Well, does that factor? You should be suspicious that things should factor out nicely. It's t squared plus 2 squared. So you end up with t cubed times t squared plus 2, or you end up with t to the 5th plus 2t cubed. So that is the magnitude of r prime. And this says this problem is great for algebraic, because what is a sub t? Well, take the derivative. 5t to the 4th plus 6t squared. All right, So there's our a sub t. Now, what comes next? Well, for the next part, we need to do our a sub n. So for that, we need to find our double prime. So our double prime of t, that would be 5t to the fourth, comma, 8t to the third, comma, 6t squared. And now, we need to take the magnitude of r double prime squared, and we're going to subtract our a sub t squared. Okay, well, this will become, and now we just have to be really patient here. So if it's the magnitude of r double prime squared, it just says you square each entry here. So it's 5t to the fourth squared plus 8t cubed squared plus 6t squared squared. Then we're going to subtract 5t to the fourth plus 6t squared squared. So that would be 25t to the 8th plus 64t to the 6th plus 36t to the 4th. And here, we're going to square this out and then subtract it. So it would be this first term squared, so that's 25t to the 8th. Our cross terms, so that would be 30t to the 6th times another 2, because it's 2ab. So that's subtract 60t to the 6th. And then the last term would be minus 36t to the 4th. And if you look, nice things happen. Well, they should. We've lived a good, clean life. So nice things should happen. So a lot of cancellation. In fact, the last two terms combine to give us 4t to the 6th. Now remember, this is not a sub n, but really what's happening is that this is a sub n squared. So a sub n squared is 4t to the 6th. And therefore, our conclusion, take the square root, is that a sub n is 2t cubed. So that's our tangential and our normal components. All right, good. So you are creating a special plate to be installed in some machinery at your company. Now the plate is modeled by a rectangle where you have that x goes from 0 to 1 and y goes from 0 up to some place b, to be determined. And moreover, the density of the plate satisfies that our density, xy, is x to the a, y, where a you can set to be any specified value. Now, what are we after? We're after a plate which has a center of mass at the location 1/3, 2. So let's say this is at 1/3, this is at 2. This is where we want the plate to balance. So the question becomes, how do you pick A and B so that will be your center of mass? So we need to review center of mass. So center of mass, we do what? Well, x bar is going to be our moment, my, over m. And y bar is going to be another moment, mx over m, where here the subscript refers to axes. So this is the moment with respect to the y-axis, this is the moment with respect to the x-axis. But in some sense, that's sort of not the most critical thing. The real idea here is to say, all right, it's just a bunch of integrals where we're going to take a weighted average. Now, can we use symmetry on this problem? And the answer is no, unfortunately not. The problem is that while our shape does have symmetry, and it's a good shape because, for example, if you cut it, say, there, or you cut it, say, there, the density does not share that symmetry. And since the density doesn't share that symmetry, we cannot use any symmetry, which means that we really get a full set of 3 integrals to work on. That's okay. So we can do that. So what do we have? Well, let's do our mass integral first. So mass, the way you compute mass is you always do mass the same way. It's the integral over your region of density. So that's two-dimensional, three-dimensional, one-dimensional, it's always the same idea. If you want to find mass, integrate density. All right, so for us, what does that become? Well, our region is x goes from 0 to 1, y goes from 0 to b. Our density is x to the a times y, and we set it up as dy dx. Now, this is one of those integrals where you can really separate it fairly straightforward. So this becomes the integral 0 to 1 of x to the a dx, integral 0 to b of y dy. Because our bounds are fixed numbers. If your bounds are numbers and your function can separate as multiplication, pull it apart. So the first integral will be 1 over a plus 1, x to the power a plus 1, and you evaluate from 0 to 1. And so that's going to end up being 1 over a plus 1. The second integral is going to be 1/2 y squared. Evaluate that from 0 to b. And if you do that, you're going to get 1/2 b squared. So there we go. So there's our mass. Now let's think about our moment. So if we do our, say, moment with respect to our x-axis, well, the moment is referring to an axis, which means that you incorporate a distance. So moments have a distance aspect. So how far are you from the x-axis? Well, the answer is y. So it's distance times density dA. So if you look, the only thing that happens is that we go from y to y squared. So that means that we can have the same basic setup. I'll go ahead and skip a step here. But it's integral 0 to 1 of x to the a, integral 0 to b of y squared. So what's the change? Well, the first integral is still 1 over a plus 1. The second integral is now 1/3 y cubed. And then we're going to evaluate that from 0 to b, so we end up with 1/3 b cubed. The m sub y will be the integral over our region x times density. So here what happens is we're adding a factor of x. So instead of x to the a, it's x to the a plus 1. So 0 to 1, x to the a plus 1, dx 0 to b, y squared dy. So the change is that now instead of 1 over a plus 1, it's 1 over a plus 2, but it's still 1/2 b squared. So there we go. There's our moments and our mass. And now we just say, okay, suppose we take our x bar first. We know we want that to be 1/3. That should be our m sub y, which is 1 over a plus 2 times 1/2 b squared. Divide that by our m, 1 over a plus 1 times 1/2 b squared. And you'll see that the 1/2 b squared doesn't make any difference. So those are just going to cancel out. So if you flip the 1 over a plus 1, so you get a plus 1 over a plus 2. Cross multiply. So if we now cross multiply, we get that a plus 2 equals 3a plus 3. We can move the a across. We can move the 3 across. And so we end up with 2a equals -1, or a equals -1/2. All right. All right, it's possible. It's possible. Why not? Now, for the other one, which is the y bar, that should be at 2. That's our m sub x. So that's 1 over a plus 1 times 1/3 b cubed, and divided by m, which is 1 over a plus 1 times 1/2 b squared. Well, here the a plus 1's cancel, and 2 of our b's actually cancel. So what are we left with? Well, we're left with, if we clean this up, 2/3 times b. And now, well, that's pretty easy to solve for b. Divide both sides by 2, multiply by 3, you get b equals 3. So our final answer is -1/2 for a and 3 for b. All right. Good. Okay, number 10. Convert the following integral in cylindrical coordinates to an integral in spherical coordinates. Do not evaluate. Well, c'est la vie, such is life. So we know we have something in cylindrical. We want to get to something into spherical. So there's a couple things you want to make sure you account for. You want to account for the dv. You want to account for the function. And then you want to account for the bounds. All these things have to happen. Now, in cylindrical coordinates, your dv is r dz dr d theta. Notice what's not here. There's no r. So, what we should do before we do our full conversion is we're going to rewrite this as the following, as z squared over r times r dz dr d theta. So that part is our dv. Okay, so now we have that. That's going to become easy to convert. In fact, when we go into spherical coordinates, what does dv become? Rho sine of phi d rho d phi d theta. Right? Right. Good. 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 Yeah, we can remember that. Now, that's the function. Sorry, that's the dv. The function part, that's the next part. What do we do next? Well, we have to rewrite everything in terms of rho, phi, and theta. So we need some basic facts. So here's some good basic facts to know. Z is rho cosine phi, and r is rho sine phi. So this is useful because what do we want to do? We want to write z squared. Oh, I guess I should also add something about theta. Theta is theta. So that's the good news. So the theta that works for cylindrical also works for spherical. So if I have z squared over r, well, that becomes rho cosine phi squared over rho sine phi. Or if you like, that's rho cosine squared phi over sine phi, because you can cancel off one of the rows. So there's our expression for z squared over r. So that's our function part. And don't get too worried about the sine phi there, because you can see that we're going to do a cancellation with the sine phi once we put it all together. So there's our dv has been taken care of, our function's been taken care of. Now we come to the bounds. So the bounds are fun. First off, notice that because nothing in here depends on theta, and we're told theta goes from 0 to 2 pi, what that tells us about our shape is that it's going to be rotationally symmetric. In other words, we're going to spin this all the way around. It's going to be the same thing regardless of where we end up. Okay, so that's good. We just need to figure out what to spin around. To do that, let's think about what happens in the, what I like to call the RZ plane. Well, we're told that r starts at 1 and goes to square root of 2, because that's our bounds for r. And now, where do I go? Well, the top is z equals r, so I'm going to go up to the top, z equals r. The bottom is the square root of 2 minus r squared. Well, the square root of 2 minus r squared, if I think about what that curve would be, in the ZR plane, which is where I'm drawing, that's a circle of radius root 2. So, let's see, have I drawn this correctly? Yes, I have. No, I haven't. That's the danger. We like to give pictures on the test. All right, I do have the right setup. It is 1, it is root 2. But what's going to happen here is it turns out that you cross. So this is the line z equals r. Here's the curve z equals square root of 2 minus r squared. And we are going in here. So to get our shape, we spin that around. Now, it's not entirely clear per se what that shape looks like. If you spin this piece, this edge here, what do you get? A cylinder. So in some sense we could say, okay, so you have a part of it, there's a cylinder here. Then you have this line. If you spin this line, what are you forming? A cone. So we have a cone as well. So it's like you have a cylinder. You took out the cone out of the middle. All right. And then what else do you have? Well, the circle, when you spin that, what do you have? You get a sphere. So there's a sphere here. So what you've done is somehow you've taken that shape that would result when you spin that around. I don't think that has a name, but that's okay. It doesn't need to have a name. We just have to have a descriptor. All right. So we have something. We have something. Now, let's see if we can put everything together and get our final answer. And it feels like we haven't done anything yet, but that's okay. We'll do it live, as they say. And write it down. So we're going to take our function. So that's rho cosine squared phi over sine phi times our dv, rho squared sine phi, d rho, d phi, d theta. Theta is going to do the same thing in both settings. So if I'm going 0 to 2 pi, I still go 0 to 2 pi. If I go 0 to pi, I still go 0 to pi. Whatever you do in one, you do in the other, because theta represents the same thing. Now we come to our phi. Phi says, what happens after you come off the positive z-axis? So what happens is nothing until we hit the angle corresponding to that cone. Which angle is that? Yeah, 45 degrees, pi over 4. So we start at pi over 4, and we stop when we hit what angle? Pi over 2. Because remember, our angle is off of the z-axis, not off the x-axis or r-axis, or whatever you want to call it. So it's how far do you come off that axis. Now, suppose I come down some angle phi. What I need to do is figure out what's happening to rho. And I like to use this picture because it's very illustrative. And I say, well, I come out from the center, and then I hit something, then I hit something else. I want to see what those two things are. Well, the first something I hit, what's that first something? What's that surface? It's that sphere. In spherical coordinates, how do I describe that sphere? As rho equals square root of 2, because that's the radius of the sphere. And then I go all the way out till I hit the edge of the cylinder. Now, the cylinder, that's a little bit more subtle. So this is, the cylinder would be r equals square root of 2. Well, I know what r is in terms of rho and phi. So square root of 2 is equal to rho sine phi. I need to solve for rho because I'm doing rho bound. So I need rho equals 2 to rho equals something. So rho would equal square root of 2. If I bring the sign across, what does it become? Cosecant. 1 over sine is cosecant. So square root of 2 cosecant phi. Now we can clean this up a little bit. I mean, not much. This is perfectly fine. So 0 to 2 pi, pi over 4 to pi over 2. The bounds, they're done. They're not going to change. Root 2 to root 2 cosecant phi. The one thing you can do, though, is you can say, well, look, I can cancel a sign, and I can put the rows together. So you get rho cubed cosine squared phi d rho d phi d theta. And that is our new integral. And we only had to set it up. So this is testing, okay, can you think in spherical coordinates? Can you think in cylindrical coordinates? What do things look like? All right. Use the method of Lagrange multipliers to find potential locations of local maximums and minimums of the function f of x y equals root 2 times x, given that x to the fourth plus x squared y squared equals 48. Now, I'm being a little bit hesitant in hedging my bets by saying potential locations instead of saying find the locations. Because Lagrange multipliers, technically, all you're doing is finding where they might be they do not actually tell you whether or not it's a max or a min. For the exams, we are not going to test you on whether or not you prove something is a max or a min. So if we say find a max, there really is a max. And even if there's not, pretend like there is. And similarly, if there's a problem about find the min. So how do you know what to do? Well, this problem is basically telling you you need to do Lagrange multipliers. So how does Lagrange multipliers work? It's the following setup. If I have f of xy, which I'm trying to optimize, so this is, I want to optimize f of xy, and I'm given that g of xy is equal to some value c. And then what we do is we set up a system of equations, say f sub x equals lambda gx, fy equals lambda gy, and then g equals c. So we solve for the points in this system of equations. All right, I'm going to ramble for just 30 seconds here because it's been a while since we've done this, and I just want to make sure we haven't totally forgotten it. And I know we have a week and a half to remember it, so let's just take that time to remember. The geometry here says you really want the gradient of f to be parallel to the gradient of g. That's what you're after. And so that's what these first two equations say. The lambda is, because you want them parallel, it just means it's a constant multiple. You really, in some sense, don't care about lambda because the value for lambda has no effect on what you do later on. So what that tells you is there's a good strategy. It sounds sort of counterintuitive, but start by solving for lambda. So if you can solve for lambda early, then that helps you to remove it out of the equation, and it reduces down to two equations involving x and y. And in particular, that you should think of the first two of these is going to end up producing a new relationship for x and y, which when you combine with the original constraint, gives you enough information to solve for your points. All right, back to our regularly scheduled problem. So we have our function here. So we say f sub x is square root of 2, and that's going to be equal to lambda. And by the way, in case I haven't said it yet, this is g of x, y. This x to the fourth plus x squared y squared. So that's equal to lambda times g sub x, which is 4x cubed plus 2xy squared. And f sub y, which is 1, that's going to be equal to lambda times g sub y, which is x squared times 2y. All right. But when I say solve for lambda, what I mean is just that. I'm going to take lambda, and I say, well, in the first equation, that's the square root of 2 over 4x cubed plus 2xy squared. And in the second equation, that would be 1 over x squared times 2y. Now, well, let's cross multiply. Get rid of our fractions. So we're going to get 2 square root of 2 x squared y is equal to 4x cubed plus 2x y squared. Now at this stage we'd like to say it'd be nice if we could cancel something. And so let me ask you the question. Can we cancel something? Can we cancel 2x? Well, we can divide by 2x if we're sure that our answer will not be that x equals 0. Could x equals 0 be a potential answer? Well, no, because notice if we plug in x equals 0, what do we get? We get square root of 2 equals 0 and 1 equals 0. So we know that, look, x equals 0 is not going to be a solution. So it's okay for us to divide by 0 in this case. So we get that 2 square root of 2y. That's equal to 4x squared plus 2y squared. And I can even tell when I wrote it down that I should have said, whoops, I should have been dividing by, oh, there's an x here. I should have been dividing by the 2 as well. So square root of 2 times xy equals 2x squared plus y squared. Well, let's move this across. So we get that 0 equals 2x squared minus square root of times xy plus y squared. Now, what would be great for us? Well, what would be really fantastic for us would be if what happened right there. This 0 equals 2x squared minus square root of 2xy plus y squared did what? Yeah, that would be great for us. Does it factor? If it doesn't, then I've made a mistake somewhere. Come on, mistake, where are you? We might be stumped here. Should have been a 2. Okay, so what does that change? The good news is it doesn't change very much. That should be a 2 there. And that means that that should be a 2 there, which means that this should actually be a 2 times 2 root 2, which is still a 2 times 2 root 2, which is still a 2 times square root of 2 xy, which means that this is now a 2 times square root of 2 xy. Okay, now we're ready. Okay. It helps when you actually do the problem right. What happens from here? Now from here, it looks not great, but actually, check this out. This is really square root of 2x squared minus 2 times square root of 2x times y plus y squared, which means this actually factors square root of 2x minus y quantity squared. So, what are we going to get from this? Well, from here, we come to the conclusion that y has got to be equal to square root of 2 times x. Now, suppose we have that information. So y equals square root of 2 times x. Then what happens? Well, from here, we plug that into our equation. So that tells us that x to the fourth, and when I say that equation, our constraint, x to the fourth plus x squared times 2x squared equals 48. Or 3x to the fourth equals 48. Or x to the fourth equals 16. Well, that's pretty good. That we can solve. So we're close. We're close. So when does x to the fourth equal 16? The answer is when x is either plus 2 or minus 2. So two possibilities. So we're left with two potential points. So at x equals 2, then y would be equal to 2 times square root of 2. And at x equals to minus 2, so you get minus 2, and you get minus 2 times square root of 2. So when we were looking for potential locations, that's our answer. These are the potential locations. So it might be the case that we are maximized and minimized at these points. Now, you've got to be careful here, because you want to say, oh, so does that mean that these are where the max and mins occur? And the answer is no. There is no max and min. But these are local max and mins. If you were to plot the curve, x to the fourth plus x squared y squared equals 48, what you would see is it looks vaguely something like this. And what we've discovered is we've discovered 2 points on our curve, and I don't know exactly where they are. Let us, for sake of discussion, say it's these 2 points here. They're sort of opposite in some sense. Now, what we can see is if I'm looking at expressions where x and y, I can see, well, if I want y to be large, I just go way up. If I want y to be really large negative, I go way down. So that says that this function, this 2 root 2x plus y, can get arbitrarily large. But what's happening is that it's locally having a min or a max at these two locations. So this is one of the downsides of the Lagrange multiplier. But here's the beautiful thing. You will not need to worry about the downside. If we ask you for a maximum, there will be a maximum. If we ask you for a minimum, there will also be a minimum. So we're only going to ask you for things that you can do. And we'll also ask you for problems where we make sure we've checked so that we get the right problems, so we don't get stuck, because that would be terrible. Yes, it would. All right. Well, back to the next one. Number 12, which now, after Lagrange multipliers, makes me really nervous. So, because I put this into Wolfram alpha and it couldn't do this one. And so, but we're going to try it. We're going to go for it. And 2 strikes, and oh my gosh, I'll be in trouble. Well, there aren't that many problems left. Let G be the surface. F of xy equals 1/3 x cubed plus 1/2 y squared over the region 0 less than or equal to x less than or equal to 1 and 0 less than or equal to y less than or equal to 2. Find the integral on the surface of G of 24zy minus 12y cubed dsa. Now, how do we do this? Well, this is a surface integral. How do we know it's the surface integral? Well, because we are integrating on the surface. So that's a pretty good clue. That's the surface integral. Now, the way we actually do surface integrals, if it's not a flux, is we've got to sort of bite the bullet and say, all right, the way that this happens is in general. So if I have my surface is of the form f of xy over a region, it becomes the integral over my original region. And what I do is I rewrite the function in terms of x and y. I have to figure out what that becomes. And then after I do that, the dsa becomes the square root of 1 plus f sub x squared plus f sub y squared, dA. So this little piece on the end, this is the part that came from the surface area formula. So that's how we do these types of surface integrals. So for us, let's not... well, the region is just a square. It's a rectangle, so that's not so bad. So we got to write our function in terms of x and y. Now, you might say, hey, how do you handle the z? So what's the correct answer? How do you handle the z? Right, we plug in f of xy. So before I do that, I'll go ahead and factor out things that are common. They both have 12y. So I get 12y. And if I do that, what am I left with? Well, I'll have 2 times z, so 2z minus y squared. And I'll go through and I'll keep working on this in a second. It'll take a while. F sub x, what is f sub x? X squared, and then we square that. And then f sub y is y, and then we square that. So dA, region R. Okay, now we'll get serious. Okay, if I take 2 times z and I subtract y squared, what am I left with? Well, that'll be 2 times 1/3 x cubed plus a half y squared minus y squared. Because I just replaced z by the function. So we're at 1 plus x to the 4th plus y squared. And I'll still do dA until I get this cleaned up. So the 2 times a half y squared is y squared minus y squared. So those cancel. So I really have a 2/3 times 12. 2/3 times 12 leads us to 8. So integral of 8 yx cubed square root of 1 plus x to the 4th plus y squared. And now I'll do proper bounds. Let's say dx dy. So y goes 0 to 2 and x goes 0 to 1. All right, so that's the integral. So we've actually set it up and it said the surface integral becomes an integral over your region R. So that's something you should just know. And how do you do it? You just remember, okay, write everything in terms of the function, x and y. Anytime there's a z, replace it by the right function. Your dsa piece becomes that square root of 1 plus fx squared plus fy squared. Okay, so that's not so bad. The bounds are, do what you normally do for bounds. Now, is this an integral that we can actually do? And the answer is, yes, we can do it. So let's work on the inner layer. So on the inner layer, what do we do? Well, we're going to set u equal 1 plus x to the fourth plus y squared. And we're thinking here of, currently we think of y as a constant, because in the inner layer, that has nothing to do with y. Y is fixed. So the variable is just x, so that's 4x cubed. This is not u as a multivariable thing, it's just saying x to the fourth plus this other stuff. Well, I happen to have a lot of x cubed sitting around. So that's very convenient for our purposes. Very, very convenient for our purposes. So I can think of this 8 as really 2 times 4. So we get 4x cubed dx. So what do we get? Integral 0 to 2. Integral. So we have a 2 and a y. That's still going to be around. 2 and a y. And now this square root of 1 plus x fourth plus y squared is u to the 1/2. And then times it by du, because that's the 4x cubed dx. So that's our du. Now, where are the bounds from? Well, the bounds go from, we plug in x equals 0, where you get 1 plus y squared. When we plug in x equals 1, we get 2 plus y squared. So from 1 plus y squared to 2 plus y squared. So 2y is a constant. So what do we end up with? Well, we integrate u to the 1/2, and that would give us 2y times u to the 3/2. And then in front, we're going to do the reciprocal, 2/3. So evaluated from 1 plus y squared to 2 plus y squared. And then that, we'll do that. Oops, sorry. Yeah, that was right. I just forgot my dy in the end. And this integral is dy. So, what do we have? Well, this becomes the integral from 0 to 2 of 2/3, and I'm going to leave it as 2y. You'll probably see why in a second. 2 plus y squared to the power of 3/2 minus 1 plus y squared to the power of 3/2 dy. All right. Now what do we do? Well, let's make another substitution. We'll do a little bit more tightly controlled. U equals y squared. Du would become 2y dy. So we have a 2y dy. So if we do this integral, well, I'm running out of space over there. I'll start working on this other side. This becomes 0 up to 4. And we'll have a 2/3. Still sticks around. And then we have the 2y dy becomes our du. And then we have our 2 plus u to the 3/2 minus 1 plus u to the 3/2 du. And these are both integrals we can do. In fact, these are the kinds of integrals that you really don't even have to do substitutions for by this stage. We want you to be able to do these integrals without substitution. If you need substitution, that's okay. No worries, no worries. So we get 2/3, and here we'll have u plus 2, or 2 plus u, doesn't really matter which order you go into, the 5/2, and then we're going to multiply this by 2/5, and then we're going to subtract. I'll multiply this out, 2/3, and then here it'll be another 2/5, and then it'll be u plus 1 to the 5/2 power. And then we're going to evaluate from 0 up to 4. Well, I should just plot that constant, so that's 4 over 15. Then when I plug in 4, I'm going to get 6 to the 5/2 minus 5 to the 5/2. So that's, plug in 4 for u, plug in 4 for u. And then from here I'm going to subtract, plug in 0. That'll be 2 to the 5/2. And then subtract this, and there will be a minus minus, that ends up being a plus. 1 to the 5/2, which is 1. And that says 4/2, that should say 5/2. Yeah, so there you go. 6 to the 5 halves minus 5 to the 5 halves minus 2 to the 5 halves plus 1 times 4/15. And yeah, Wolfram Alpha couldn't find this answer. So, oh well, good. Phew. At least we can do one problem. All right. A few more. Don't worry, these last ones will go pretty quick. Let G be the surface of the cylinder x squared plus y squared equals 4 for 0 less than or equal to z less than or equal to 3. And let n be the outward pointing normal vectors. Find the integral on G of del cross y minus e to the x, comma xz squared plus 5y, comma log of z plus 1 plus 7xy dot n dsa. Now, what do you have? Well, you have a surface of a cylinder, but in particular, it's the following. It's x squared plus y squared equals 4 for 0 less than or equal to x less than or equal to 3. So it's not a solid cylinder. It's a cylinder, just the shell of it. So we're just talking about the side of the cylinder. It's not the top, it's not the bottom. There's also these ends, and the ends point out. So, for example, on the sides there, it's pointing out. On the front side, it would be pointing towards us, and the back side would be pointing away from us. So we have this oriented surface. And the question becomes, well, what's our right problem, or what's the right tool? And here, and I know you haven't quite learned this yet, but I'm going to point out that there's a giveaway to what to do. You see there a curl, del cross. When you see a curl, that tells you that this problem has to be Stokes. Stokes is basically the only thing that's showing up where a curl is involved inside an integral. So in particular, when you're doing Stokes theorem, what's actually happening is you're finding the curl, you're finding the flux for what's the curl of this vector field. Now, the problem with this vector field is that it's tough to work with. So we have a couple of choices. One choice is we can say, all right, let's just integrate on our boundary of our surface, just our function here, whatever that is, and we'll call that dot t ds. That's what Stokes theorem says, as it's written down. Now, where's our boundary, and how much is there? Well, our boundary actually has two pieces, because there's two places where you have the edge of that cylinder. So there's two parts. That's okay. You can have multiple parts of the boundary, but we'd have to set up a boundary for each part. Again, that's okay. Sometimes that happens. Now, my favorite thing to do with Stokes theorem, and I keep doing it over and over again because it works like 95% of the time, and we like to test on things which are fairly common, or at least work pretty well, is to say, let's choose a better surface. I like to call it BYOS. Bring your own surface. So, all right, so we're going to just change the surface that we're working with. Now, when we change our surface, we're not going to necessarily change the boundary. In fact, we can't change the boundary. The boundary has to stay the same. We just have to say, look, given that I have the same boundary, what's a better surface? So, our boundary, we're a pair of circles. What's a better surface for a pair of circles? Do you see a nice surface that works? Well, the answer is put in two circles. Put a solid field in a circle there, and you put a solid field in a circle down there. And if you do that, yes, that's a surface. It's a disconnected surface, but that's okay. You're perfectly allowed to have disconnected surfaces. The only thing that's important is that the boundaries match. Now, there's one other thing, which is orientation. And so how do we figure out the right orientation? Well, here's one way I like to think of it, is because you can bring your own surface, what you can do is you can think of the following. So if I start with my original cylinder, and what I'm going to do is I'm just going to say, let's follow this normal vector, say, on the side. So I'll follow a normal vector here as well. So I'm going to just sort of start pulling it in. And if I pull it in a little bit, I'm still pointing more or less in those ways. So pull it in a little bit more. Now the one up here is pointing very down, the one downstairs is pointing very up. And now eventually you pull them and you separate it, so it's like you're popping it. And you say, okay, now this one is definitely pointing down, this one is pointing up, and then you push it all the way in. So what you get is that the orientation says that for the top one, you should point down, 0, 0, negative 1. And for the bottom one, you should point up, 0, 0, positive 1. Now, this is why I like to do flat things. It's because the normal vector becomes really, really clean. When your normal vector is really, really clean, it makes it so much easier to work with. So, let's compute the curl. So when we take the curl, which entry do we care about? The z entry, like the third entry, right? So we're going to take this curl, which I, j, k, partial partial x, partial y, partial z, of y minus e to the x z squared plus 5y, and this terrible looking expression which is there to distract us, to make us think it's hard, so that we're going to skip this problem. But really the points are there for us to be had, and we want all the points. So what are we going to end up with? Well, we're going to end up with something, something. Now, come to the last part. We have k partial x of xz squared. Well, what's that? Z squared. And in the other direction, we have k partial y 1 of y, which is going to be 1. Got to subtract 1. So you get z squared minus 1. Okay. So that's our curl, at least the one part we need if we can get to use our flat shapes, which we will. So let me be really careful here. I want to point something out. Remember we said that 0 is less than or equal to z less than or equal to 3. So z equals 0 is the bottom. Z equals 3 is the top. So down here, this is still z equals 0, and this is still z equals 3. And let's label these two disks. Let's call this disk, we'll call it capital A for the first, z equals 0, and capital B for the second as z equals 3. So we get that this becomes the integral over A of something, something. Now, if I'm on A, what's true about Z? Z is 0. So what happens to Z squared minus 1? Becomes negative 1. So it actually looks like it, oh my gosh, it's going to vary steep, but no. Because I'm at a place where Z equals 0, so it's not varying at all. I'm going to dot it with my normal vector, 0, 0, 1. And then I'm going to take this dsa, we'll figure out what that is, plus the integral on b. So here, what's true about z? Z equals 3, so z squared minus 1? 8. And we're going to dot that with 0, 0, minus 1. So the first thing, if you multiply it out, you're going to get negative 1. So you're going to get minus 1. And then you get the area of A, because you get integrating dsa. On the second one, you multiply it out, you get negative 8. And then you get the area of B. Well, let's look at these circles. What circles are they? Well, they're the circles for x squared plus y squared equals 4. How much area is in one of these circles? 4 pi. So we're going to get this part is 4 pi. And this part is 4 pi. So we get minus 4 pi, minus 32 pi, or negative 36 pi. So once you get the hang of these problems, they can be very easy. But you got to get the hang of them. So you got to practice. And the good news is we are going to do lots of practice. The practice is coming. The practice is coming. Find the curl and divergence for the vector field h equals x cubed plus z e to the y times I plus log of y squared plus 1 minus 2xz squared times j plus 5xyz times k. Notice we can give vector fields in two different ways. We can either give it into this format, or of course we can write it as x cubed plus z e to the y, comma, log of y squared plus 1 minus 2xz squared, comma, whoops, I need my parenthesis there, 5xyz. So either way is perfectly fine, and be ready to say, oh, I recognize it regardless of which way you write down the expression here. Okay, well, from here, what happens? Well, we do the following. We want to find the curl and the divergence. I'm going to start with divergence because that's easier. Even though it's a longer word, it's a simpler process. So the divergence of h says, go through each entry and take the partial derivative. So I go to the first entry, take the derivative with respect to x. Well, that's 3x squared. Go to the second entry, take the derivative with respect to y. The 2xz squared goes away, so that'll be derivative of log of y squared plus 1, which is 2y over y squared plus 1. And in the last entry, take the derivative with respect to z, and that'll be 5xy. And that's it. Remember that the divergence should be a function. So if your output is not a function, something has happened. And go back and undo that something. Okay, how about curl? Well, curl, we have to bite the bullet. We've got to do the whole thing. I, j, k, partial x, partial y, partial z, x cubed plus z e to the y, natural log of y squared plus 1 minus 2xz squared, and 5xyz. So we just work our way through. Partial derivative with respect to y of 5xyz, that's 5xz, that's in the I direction. Take the derivative with respect to z of x cubed plus z e to the y, that's e to the y, that's in the j direction. Take the derivative with respect to x of log y squared plus 1 minus 2xz squared, well, that's minus 2z squared, and that's in the k direction. All right, now we go in the other way. So here, we're going to take the derivative with respect to y of x cubed plus z e to the y, and that would be z e to the y, and that's in our k direction, and we got to subtract because of the direction we're going. Come here, we're going to take the derivative with respect to z, log y squared plus 1 minus 2xz squared, and that would be minus 4xz, and that's in the I direction. But because we are in the wrong way, remember it's minus a minus, so it really becomes a plus, 4xzi. All right, and let's see, what's left? 5xyz, partial x in the j. All right, so take the derivative with respect to x, you get 5yz. But because we go the wrong way, you subtract. So we put these things together. The nice thing is the first part combines nicely, so that's 9xz. Then e to the y minus 5 times yz, and then the last part minus 2z squared minus z e to the y. And that's it. You're done. That's the divergence and the curl. That's pretty straightforward. Maybe too straightforward. No, that's not so bad to be too straightforward. All right. A solid is described by the pair of equations, 1 less than or equal to x squared plus y squared less than or equal to 4, and 0 less than or equal to z less than or equal to the square root of x squared plus y squared. Given that the density of the solid satisfies the density of x, y, z equals 3 plus z, determine its total mass. So 1 less than or equal to x squared plus y squared plus z squared less than or equal to 4 tells us what? Well, it tells us we're between two cylinders. So you have one cylinder of radius 1 that's inside of another cylinder of radius 2. So we have these sort of two nested cylinders, and we're in between those two. And at the same time, we're also going to be underneath the cone. So we have this cone, 0 less than or equal to z less than or equal to the square root of x squared plus y squared. So our shape is we're spinning this sort of trapezoid, and when we spin this trapezoid around, that's what we end up forming, is this shape. So let's look in the ZR plane just to, again, nail down what we see. So we go here, really this tells us R goes from 1 to 2, and then we're going up from 0 up to R. Now, the question becomes, should we do this in Cartesian coordinates, spherical coordinates, or cylindrical coordinates? And what's the answer? Cylindrical, yes. First off, there's lots of this beautiful symmetry with respect to spinning around the z-axis. So it's very clear we do not want to do Cartesian. That's just, Cartesian is not set up for that. Cylindrical and spherical both can handle that pretty well. But the thing that makes this sort of a slam dunk case for the cylindrical is the fact that we have cylinders and everything really is being described in terms of x squared plus y squared. The other thing is it gets really messy if you try to do this in spherical. So we're not going to. All right. So what do we get? Well, so we get that mass is the integral of density, dV, over our solid S. So that's going to be integral, integral, integral. 3 plus z in cylindrical coordinates becomes what? Just kidding. It's 3 plus z. Yeah, because in cylindrical coordinates, z is still z. That's the nice thing. You don't have to do any weird function. dv becomes r, dz, dr, d theta. Because we're all the way around 0 to 2 pi for theta, we can see from the picture r goes from 1 to 2. And also that z goes from 0. So if we think about a slice up here, z goes from 0 up to z equals the square root of x squared plus y squared, which is really z equals r. So that's our integral. We can save ourselves a little bit of work and say, hey, at least the d theta, you can push that all the way in to there. So that integral would be our 2 pi, integral 1 to 2. Then we're integrating the next term with respect to z. So that's r times 3z plus 1/2 z squared. Evaluate that from z equals 0 to z equals r. Well, when you plug in 0, you get 0. That's always a good thing. So 2 pi integral from 1 to 2 of r times 3r plus 1/2 r squared. So that's 2 pi integral 1 to 2, 3r squared plus 1/2 r cubed. So that's 2 pi, and we integrate. That'll be 3/4. Sorry, not 3/4. That's just r cubed. Sorry about that. R cubed. This is where we get a nice power in. So that's r to the 4th times 1/8. So r cubed plus 1/8 r to the 4th. Evaluate from r equals 1 to r equals 2. When you plug in 2, well, you're going to get 2 pi, and you get 8 plus 1/8 times 16, which is 2. Then you're going to subtract 1 plus 1/8. So, well, I don't know if I want to say much more. 8 plus 2 is 10 minus 1 is 9, so you get 2 pi times 9 minus 1 over 8. And if you wanted to, you could say since 9, you multiply that by 8 over 8, that's 72 over 8. So you could say that's 2 pi times 72 minus 1, which is 71 over 8. And divide the 2 through, so you get 71 over 4 pi. But you probably could have stopped a few steps earlier, and that would have been fine. All right, almost there, almost there. I hope the last few are good. Okay, let C be the curve, which starts at 0, 0, 0, and ends at 1, 1, 1, and is parameterized by t to the b, t to the 2b, and t to the 3b, where b greater than 0 is some parameter. Determine the minimum value of this integral, in particular, which b minimizes this expression. So you have this whole set of curves that you could move along. The answer is, what's the right choice to pick? All right? So that's our goal. Figure out what's the right choice for b. Now, what should we be suspicious of? Maybe they're trying to distract us. Let's look at this integral. This looks like it could be something which is potentially conservative. And this is like find the minimum value. Maybe that's all there to distract us from the fact that there's an easier answer. So whenever you have a line integral, you should always sort of say, could it be a conservative integral? That should always be your first thing. It's like, can this be conservative? Because if it is, life is easy. So let's start. So we're looking for sort of the quote-unquote antiderivatives of each piece. So I come here, this should be the derivative with respect to x, so I integrate with respect to x, and what do we get? X squared yz plus x cubed. Then we go to the next entry, and this should be the derivative with respect to y. So we integrate with respect to y, and we get x squared yz plus z e to the y. And then we go to the last entry, and the last entry should be what happens when we take the derivative with respect to z. So we integrate with respect to z, we get x squared yz plus z e to the y. So in other words, I'm thinking of whatever's in front of the dx, integrate that with respect to x. What's in front of the dy, integrate that with respect to y. And what's in front of the dz, integrate that with respect to z. So what we're looking for is consistency. So for example, z e to the y, it better be the same both in the y and z pieces. If it's not, you're done. It is. X squared y to the z better be the same everywhere that involves x, y, or z. So in other words, you're just sort of scanning to see, do things line up? And as long as they match, that means, okay, that part is fine. The x cubed, I only need to make sure it works for x, and that's fine, because it's only showing up in x. And since everything is more or less, for a better word, compatible, that says that this is conservative. In fact, not only is this conservative, we know that our potential function, I'll call it little f of x, y, z, we just put the pieces together. There's really three pieces. There's the x squared yz plus x cubed plus z e to the y. And therefore, this integral, it doesn't matter which choice of b you choose. It's always going to be the same value. So the minimum value is the same as the maximum value. It's just, what is the value? So we have to find the value. So the min, this equals the max, which equals any curve. So this becomes our function, x squared yz plus x cubed plus z e to the y, evaluated from where we start to where we end. So we plug in 1, 1, 1. We're going to get 1 plus 1 plus e. Subtract 0 and 0 and 0. Whoops, 0 plus 0 plus 0. Which becomes 2 plus e. And so that's the answer. It's the min, it's the max, it's always the same. It's a conservative line integral. So be on the lookout. If you see a line integral, always test to see if it's a conservative one. Now this is our last problem, other than the one that I couldn't do earlier. But this is the last one we'll do. And let C be the solid cylinder. Now, I'll tell you right away, there's a key word that pretty much tells you what the problem is. If you see the word solid, and you see anything that looks like a dot n or a flux, it's going to be divergence. Divergence is the one that works with solids. So it's a solid cylinder. It's x squared plus y squared less than or equal to 3, and 0 less than or equal to z less than or equal to 5. So it's this cylinder. So it has height of 5, and here the radius is kind of a weird number. That's all right. The radius is √3. So we have this cylinder. The outward pointing normal, so that just means that the surface points out. And here the surface includes the top and the bottom, by the way, because it's a solid. So we want to find the integral of the boundary C of this thing dot n. This is a flux computation. So whenever you see something dot n, that's can be interpreted as a flux computation. So according to the divergence theorem, this is the integral over the whole cylinder of the divergence. So let's go through term by term. The derivative of 2x plus sine of 2x. Well, it would be 2 plus derivative of sine of 2x to cosine of 2x. All right. Plus, go to the second entry, take derivative with respect to y. For sine squared of x, go to the last entry, take derivative with respect to z, 5. And we're doing this integral dv. Now, how do you handle something like sine squared?
Power reduction.
Power reduction. So sine squared is 1/2 minus 1/2 cosine of twice the angle. What do you notice? Well, you have a 2 cosine 2x, then you have a 4 times the negative 1/2 cosine 2x. What that tells us is that while it looks like there's going to be trig involved, the two trig parts cancel. So what's left? Well, we get 2 plus 4 times 1/2, which is 2, plus 5, which is 9. So what am I looking for? Yep, the volume times 9. Yep, so 9 times our volume. Well, how do you find the volume of your cylinder? Base times height. So the volume of the circle would be pi r squared. R is root 3, so the base is 3 pi. The height is 5. So we get 9 times 3 pi times 5, and you multiply that together, that gives you 135 pi. So these problems that I know they're very new, and I know you haven't had a lot of practice. We will do practice. I hope you do more practice with these. Once you get the hang of them, they go pretty quick. All right, thank you for being patient. I'm sorry I went so long. Good luck on the exam. And hopefully I can find the right way to do this problem for Lagrange.